Hello everyone, it's Sean from Having Fun Repairs and welcome back to this channel. This is going to be the third video in our HFR teaching series. We started out with test equipment, beginning with the digital multimeter, and then we moved on to oscopes, and at the end of the oscope video I went into Lissajous patterns on our oscope. And in this video, we're going to pick back up on that concept and actually what I hobbled together in that other oscope video. We're actually going to build out a octopus, or curve tracer is more probably the better technical term for it. And then we're going to test several components that we did not test in the previous video, and I'll get into more detail the importance of being able to have one of these as a test equipment item and a complement to an oscope. Now, I will go ahead and state, if you are following along in this video, you're doing so at your own risk, because I will be there using my SIGGEN and my oscope, and yes, there will be a voltage, albeit fairly low, 10 volts peak to peak, but there are hazards such as soldering, which you can burn yourself with, etc. So common practices when working on electronic devices in general is to have your watches, rings, and jewelry off. If you wear glasses, especially metal framed rim glasses, to either have a strap on them so they don't fall into anything you work on. But that being said, if you're enjoying this content, you let me know, you hit the little heart icon, or you leave me comments, and I appreciate every single one of them. So why don't we jump into this, and we'll start talking a little bit about what an octopus or curve tracer is. Now, online you can traditionally find many different schematics for a curve tracer that you can build yourself, such as the one that you see up in the left hand corner here, versus the one that we'll be using and build on my bench today. Now, some things to keep in mind if you were to build one like we have up here. This is using AC mains, fused input coupled to a isolation transformer, essentially, or a step down transformer would probably be a more appropriate term, but is also isolated from your mains. Okay, and the step down transformer is going to take your mains AC to a lower, safe, much lower voltage. Sometimes, depending on the schematic setup and the website you find, it can range from 6 volts to 15 volts. But make sure you read the fine details of what type of transformer you're going to use. Now, you would want to have an isolated transformer, so that way at no point in time AC mains will come over to the other half of your circuit. That's a key safety feature, along with it also being fused, which is another good key safety feature. Now, traditionally, you're also going to have some current limiting resistors as well to draw your current down to your device under test, or DUT for short, DUT, to make so that way as you remove the device and hook it back up, there's not a whole lot of current going through it, which is also the third main safety concern. So, like I said, there are many different examples and many different setups. This one uses a plug to an AC mains outlet, a safety fuse step down transformer that is also isolating you from AC mains to a lower AC voltage, and current limiting resistors, as well as where you will where your DUT, or device under test, such as passive devices. And yes, curve tracers can be used on some semiconductors, but where your passive device will be hooked up, and then how you will hook up your oscilloscope as well. Now, in my example, I will be using a function generator or signal generator, such as the one that you see up here in the left hand corner right now. So I would suggest that you have a signal generator or function generator complementary to the one that you see here. as well as an oscilloscope such as the one as you see in the corner right now. Specifically, this one's a 50 megahertz oscilloscope at 5 megasamples per second, but you might be better off, and if you have the money to do it, you need at least a 2-channel oscilloscope at 50 megahertz, but I would highly recommend you have a 2-channel oscilloscope at 150 to 200 megahertz bandwidth, and preferably 1 gigasamples per second instead of megasamples per second. But this one I'm very used to, and I've used it for years. It's got its limitations, but it is a 2-channel oscilloscope, and it also offers me to go to an XY mode, which is very important to see the devices up on the display with how we're going to test them. In my diagram, we will be using the function generator or sig generator to generate a 100 hertz signal at 10 volts peak to peak, and it will be a sine wave, which is why we have this sine wave indicator here. Okay, it'll be a 50 ohm cable with the positive going to the top, the ground or negative side of the cable coming to the bottom. We will have our device under test in between here. Positive rail going to channel 1, positive of our oscilloscope, and the negative heading towards our negative rail, channel 2, which will the positive probe portion of our probe will go here. And then you see that we also have a 10 ohm 1 watt current limiting resistor down here going to the ground, and then all the grounds from our probes, channel 1, channel 2, SIGGEN, etc., will be right here. So this is going to be our setup. Of course, this will be our X channel, and this will be our Y channel. So to give it a little bit more clarification, we'll do this, X and Y. And in order to build this device, now you could use a breadboard, but I've got these little through-hole PCBs. Now, none of these through holes are soldered to each other, so we'll have to kind of make our own little jumper wires between the components. I've got my 10 ohm 1 watt resistor. I've got a spool of I think this is 12 gauge wire. I don't really remember, might be on the box somewhere, but some insulated wire that we'll use for making our connections onto this PCB. And then we'll make use of these quasi-alligator clip style test leads, which will solder wires into it, which will become our connect for our device under test, as well as a connection point for our oscilloscope probes. It'll probably make more sense here in a little bit. Now, before I build the device, I'd like to offer to you what is so significant, a little background on why making yourself an Octopus or curve tracer is a handy kind of test equipment item complementary to using the XY function of your oscilloscope. Well, to put it plainly, a curve tracer is test equipment, like I said, one you can build yourself, that can be added to an oscilloscope, either a digital or analog oscilloscope, that provides a graphical display of the voltage and current characteristics of an electronic component. It can be used to quickly check resistors, capacitors, inductors, some semiconductors, both diodes and transistors, and under some circumstances, integrated circuits. Now, the oscilloscope must have an XY mode, as previously mentioned. If you do not have one, then this is not going to work for you. Now, what the XY channel allows us to accomplish is essentially drive the horizontal amplifier, the X channel, while the other drives a vertical amplifier, or the Y channel. The X channel is going to make a measurement of our voltage, or V, and the Y channel is going to measure for us the current. So another terminology for this is a voltage over current tester, or curve tracer, but you can also call it an octopus because that is a colloquial name for it. And the observed display that we'll see on our oscope or oscilloscope is called a Lissajous pattern. Okay, Lissajous patterns are a good way of identifying potentially unusual or unexpected, how can I put this, unusual or unexpected component signatures, how they should look on the display, and compare them with a device that doesn't really match up. So essentially what I'm saying is you often take what you think is a bad component and you test it, and then you compare it with a known good. Unless, of course, you know the characteristics of that component. And if your oscope also affords you the ability to do some voltage measurements in XY mode. Mine unfortunately does not, but you could take those characteristics and look at the data sheet for that component and compare things such as your forward and reverse bias voltages and current, etc., to determine if that component's good. But traditionally speaking, your different components are always going to display in a certain waveform with a certain characteristic, and so it does lend a hand to easily identifying problems. Now, there are 4 fundamental component signatures: resistive, capacitive, inductive, and semiconductive, which we can recognize and interpret on our oscilloscope using an octopus or curve tracer. And in this video, after we build our curve tracer here, we will look at each of those components, and then I will try to fault out those components via some destructive methods, so we could see potentially what a component would look like if it were bad. With this somewhat brief introduction out of the way, I think now is the time for me to go ahead and build out this device. If you need to, here is the diagram I came up with, and you can find similar ones online. For my build here, using my function generator or sig generator and my oscilloscope, I'll throw this up over on the camera over here as well, if that's easy. You can take a screenshot of it as needed, but it will also be available. This I will have available on my Google site. Okay. However, this training video is specifically here, so this will be a complimentary video that will not be available publicly on my YouTube channel or through my Google site. But anyways, let's get to our build. Well, with the our little PCB now made, I can briefly go over the design for you and some of the choices for what I did on this PCB. If you can see, I have two leads that are coming off this end over here. That's that way I can take my 50 ohm cable going up to my SIGGEN and attach it in this fashion over on the side as a point of termination. Okay. I chose red wire going up to this little eyelet or loop that I put in right here at the top. So that way I know this is my positive rail and that the X channel for my oscope can be attached here. And then I changed my color to blue because I wanted to identify this as the positive side leading to our device under test, and then black through the entirety of our return rail, thus black here for this alligator style clip, or I don't think you would call those alligator style clips. I can't remember what they're called, but no matter the case, we have another loop sitting right here. If this will focus. All right, we actually have two loops. The first one for our Y channel oscope probe, going to our 10 ohm 1 watt resistor, and then a bigger kind of loop right here. So that way we're not just hooking up our oscope probe on the first one. This bigger loop will be for the grounds coming off of our probes. Those can clip on here. And then of course our SIGGEN connected as like this. Pretty simple setup, and I think it will work for all intents and purposes just fine, which means that now we can take our components and just attach them via these clips right here and make some what am I trying to say here? We can look at our Lissajous patterns and make some educated determinations on whether or not our components are good. So since I've got this all connected, why don't we go ahead and set up for that? Okay, we have the oscope in the upper left hand corner here on the screen and the SIGGEN in the bottom left hand corner. We are going to set up the SIGGEN starting off. Let's do 100 Hertz at 10 volts peak to peak. Now I have my frequency step value set to 1, so we can adjust our frequency as needed. And we'll turn channel 1 on. Okay, now you notice when I turn channel 1 on, I'll turn it off from the device up here real quick. You see how we are starting to measure the voltage off of our first probe, but we're not getting a current measurement at all. So we're not seeing any shift on our oscope. Now essentially this is the first thing that gives us a bit of data to go off on. When we're testing any one of these components that I have sitting over here on the right, and this is just some that we'll do in this video, if there is an open across the component, you're going to see that flat characteristic going all the way across the screen. Now, what could we say as far as the short goes? Well, let's short out our test pins here. Let's see if I can get a better connection. Here we go. Here goes our short. And typically, when you have a short, you should have a more vertical up and down line. Now we can perhaps play with our oscilloscope a bit to see if we can get it to go a little more vertical. Yeah. This actually might be better. 5 millivolts and 20 millivolts on channel 2, 500 millivolts channel 1, 20 millivolts on channel 2. Let's open it back up and see what happens. All right, we got a flat characteristic, but you can see all that noise sitting on there as well. Okay, but the bottom line, this is to demonstrate and a short is going to have a vertical display. We see that sweep going vertically, and an open is going to have a horizontal display line. We see the sweep going from left to right. We'll set that back to 200 millivolts. Let me hook it back up. Now, for my reference, instead of it being completely vertical, I'm going to leave it right there. And I just need to make a mental note of that. So that way, as I test these components, if I see my component under test going, you know what, we'll just keep it simple. I'll set it back to 20 and we'll just call it like that, okay? Well, let's move on into component testing. We got a horizontal for an open, we got a vertical if we have a short. We can start looking at our first components. Now, I've did resistors in the previous video, but let's go ahead and look at what do we have first here. 220 ohm resistor. Let's put it between our leads and let's see what happens. There you go. I actually like the way this looks better, so let's make our references again. All right, there goes an open. There goes a short. Yeah, I think that will work. So we're on 2 volts per division, channel 1, and 50 millivolts, channel 2. Okay. And that's what I would typically expect for a resistor. Now, we do have a resistor that's of a different value, but a resistor is pretty much a linear device, okay? If you were to see something like this on your oscilloscope, and then you could basically say, hey, this is acting as a resistor. Now, of course, probably more appropriately is to take a digital multimeter or analog multimeter and measure the actual resistive value in comparison to its color bands and tolerance to see if that resistor is still within tolerance to say if it's good or bad. But let's say you just have some unmarked components sitting in a drawer, and maybe you don't know if this is a resistor or an inductor. You could throw it up on here and you would be able to see something like this and be able to easily say, okay, we got a forward upward slant. This is obviously a resistor. Now, if I replace it with a different resistor, let's see what occurs. And we pretty much get the same slant, do we not? It looks like it's not, the length of it is not as much. You see, when we have resistance, we do get slight changes. So perhaps as well, say you are, the resistor is unmarked and you don't really know the value. Well, you could take a snapshot. Again, just something to sit here and slightly theorize. You could take a snapshot of what's currently on your screen and then use marked resistors to make a same measurement to see if they appear to be the same on your display. Again, at this point in time, you're not going to change anything on your SIGGEN as far as your frequency or your amplitude. Now, one thing to note, when it does come to other components, frequency and the amplitude are going to be very important for how we do the tests. But resistors are fairly simple. And the main thing to take away is when you're looking at these curves for resistors on your oscilloscope, is you don't want them to be open, as you currently see right now, and you don't want to have any shorts, right? So that's a fairly easy way of testing resistors. Now we'll get on to something slightly more complicated. Let's look at diodes. This first one we have here is a 1N400, I think. Let's see if that's what we got written over here. Yeah, 1N401, excuse me, rectifier diode. We need to make sure that we have our anode and cathode are oriented correctly. And look at what we get on the display. This is something I would expect to see with a diode. Essentially what you have is you have your forward biasing voltage, and then it's coming up over this way. So we can see that that diode is conducting. Now again, if you have unmarked components sitting in a drawer, you can roughly make an estimate as to what type of diode you actually have, based upon how it displays. Can I lower this? I think I just messed it up some. Let me go back out of XY mode for a second and I'll come back. Okay. Taking myself out of XY mode, we now have well, let me turn these measurements off. All right, I've taken myself out of XY mode and put myself back into traditionally how you would look at an oscilloscope, and we'll kind of go over this real quick. The bottom, somewhat sine wave you see here, this is our voltage, okay? And the top one here on channel 2 is our current. Okay, and let's see what occurs here. We see as our voltage goes negative, we have no current flow because we start to, the diode starts to cut off, essentially. And as our voltage starts to go positive and we bias the diode, we can see that the diode starts conducting and we have current flow again. Now, I will take this out of back into XY mode, and it might be worthwhile to go ahead and note that channel 2 right now I have set to 2 volts, or channel 1 to 2 volts and channel 2 to 200 millivolts. Okay, and then I'll take a mental snapshot of this. Say this was an unknown diode on a board I couldn't figure out, no stamps on it. I'll take a snapshot of this, and then I could go through a pack of diodes, connecting them up until I get one that looks very similar in its pattern. As a matter of fact, when I am looking at this, I'm not seeing, well, let's make our channel 2 Let's make them both about 200 millivolts. Whew. I don't know why it's doing that. It looks pretty weird. Let's go to 500. That's probably better. And let me disconnect this for a second. Okay, and we're going to need to center that up a bit. I've essentially centered it up by taking it out of XY and putting channel 1 and channel 2 back on the middle gradical together. But we'll go back to XY mode, and our dot is essentially on the center there. And we'll connect this back, and we can essentially from the center line, counting outwards, we've got, what is this? 500 millivolts, about 750 millivolts. The diode starts conducting, if I'm reading this correctly. And yeah, doesn't take much to bias this diode, so something to keep in mind. Again, you know, unknown part, you can grab some diodes out of a box and determine what diode is you have, as well as, well, let's also consider that not all diodes are going to look exactly the same. So we'll practice that. Right now we're at 500 millivolts, channel 1, and 500 millivolts for channel 2. Let's check a different diode. This one is a, what is this? It's got a stamp 4007. So UF 4007 fast recovery diode. Okay. Now you might say that these initially look the same, but they're not. If we again look at our pattern again, we expect to see the diode to be biased and for it to conduct. So we have this leading edge coming up over here. But at 500 millivolts, we are essentially at 500 millivolts, maybe closer to about 550 or 600 before it starts conducting. So we definitely see a difference here on our Lissajous pattern concerning this diode. Now, the main thing to take away is this is what you should see when you're looking at a diode. Something like this is what you're expecting to see. But again, you can compare it, a known potential bad diode with a known good diode, to see if they look exactly the same and they bias at the same voltage for biasing voltage. And if they do and they look the same, then you know this is a good diode. But if it doesn't, potentially you have a bad diode. So a good way to test your diodes by comparing how they look. And then obviously different diodes are going to look differently. So let's look at another option. Now this one is a pretty common 1N4148 switching diode. And then going to our pattern here again, we see, what is this, 500, about almost 750 millivolts, but it's forward bias now. Now, oftentimes, if you have, if you're using something like a Zener diode in a circuit, you would actually also have a trailing edge down here, because there would be you would be able to detect the reverse bias voltage as well. Now I can kind of demonstrate that by switching this diode around. And hooking it up incorrectly. See, there you go. Well, you would see that trailing edge and leading edge at the same time with the switching, with a Zener diode. So again, the main purpose of this is do one of a couple things. You take your bad diode off the board, and if you know the part number for it, you compare it with a known good part number, known good component, and see if they look the same. All right, that's one thing we could do. We can compare the forward biasing voltage with the characteristics found in whatever data sheet for the diode. There goes a second thing. Okay, and then we can kind of determine which diode we have based off of how it appears on our oscilloscope. Now, like I mentioned, you'd be better off with a 150 to 200 megahertz oscilloscope with 1 gigasamples per second. So there are better oscilloscopes that are going to afford you a better display, and there are oscilloscopes that will actually allow you math functions while in XY mode as well. So just one thing to consider. All right. Now let's move on over to capacitors. This first one we have is a, what is this? 22 microfarad 16 volt capacitor. Well, let's consider, am I above 16 volts on my SIGGEN? No, I'm not. I'm at 10 volts peak to peak. I'm looking at my frequency. I'm at 100 hertz. Polarity is important for these electrolytics, so we gotta make sure we hook them up correctly. Actually, I want to do the bigger one first. Let's do the bigger one first. The bigger one is a, what do we got? 220 microfarad at 25 volts. Again, polarity is important. Now, what a capacitor does is it affords you a phase shift. So you see this nice, elliptical pattern we have here. This is what I expect to see of a good capacitor. Now, if your oscilloscope wasn't giving you a, it's kind of looking like it was elliptical, but it's sweeping, you can change your frequency to adjust for that. Now, thing to keep in mind, see how I changed my frequency? That you see that elliptical change as well. And we could actually back this down and get a full circle, most likely, or just about. The thing to keep in mind concerning capacitors is they're often used to filter out unwanted frequencies, right? They can be used as a high pass or low pass filter. So your frequency is going to be important when you initially set up, as well as your amplitude, that you do not exceed the rated voltage for your capacitor. Now again, we're looking at a 220 microfarad 25 volt capacitor, and if I suspect it to be bad, well, if it was shorted, what will we have? That vertical appearing line. Let me try to short it out here for you. Or we just do like this. If it was shorted, it would be looking like this. And then if it was open, it would look like this, and we would not have something that looks like this. Now, what if the markings were off on this capacitor? Would I be able to, hook up, go through a capacitor box and perhaps find something comparable to what I'm seeing on my oscilloscope? Yes, you could, so long as your channel 1 and channel 2 is not changed. Keep it at what it needs to be. So you can make a rough guess that way, although, again, you do so at your own risk. It's better to factually know what value is required for that than to guess, per se, looking at an oscilloscope. But each capacitor is going to display that oval shape a bit differently as well. So we'll take out this capacitor, and let's put in the smaller valued one for, what was this one? This was the 22 microfarad versus 220, rated for 16 volts. So again, our amplitude is perfectly fine in this case. And look, that circle is much bigger. So we would actually have to come up here on our oscilloscope and adjust our channel 1 and channel 2 ranges to be able to see it. That's something to keep in mind, I would think. Now, I kind of want to demonstrate something. When you're troubleshooting a capacitor and you suspect it to be leaky, can we demonstrate a capacitor that's leaky by perhaps damaging a capacitor? Hopefully without causing too many issues. I'm going to do something slightly destructive here, and we'll see how this works out for us. Hopefully I don't go too boom boom. Actually, you know what? What we'll do first is crimp it. I flattened it out. Now we'll hook it back up, and we'll see if that's changed our pattern at all. Ooh, and it definitely has. That does not look like what it originally looked like. Yeah, if we go back down to 500, see how that oval is kind of shifted on us compared to how it looked previously. I'll try to do a snapshot in this section because I didn't stop and snapshot it myself, but we can do a quick comparison to see that difference. So again, you know, checking a known good with a suspected bad, and you might be able to determine if that capacitor is good or bad without hooking up an ESR or you know, whatever type of handheld meter device you're looking at. Well, for kind of poops and giggles, before we go to transistors, I kind of want to look at a light emitting diode. A red LED has a forward biasing voltage of about 1.8 to 2 volts. So we're going to drop down our amplitude a bit. Let's do 2 volts. Okay. And then what is our orientation on this one? I think it's oriented this way, although I could be mistaken. I probably shouldn't guess, but we're going to take a guess. No, that's definitely not it. We need to reverse these. And maybe I need to bump that voltage back up. Let's try that. Yeah, there we go. We got it set to 5 volts. We'll step that up just a wee bit more. At 7 volts, probably could have just left it on 10. Now we're getting super bright. Let's drop it down to 6. 5, 6, 5, 6. Let's put it at 6. Okay. So we can see a light emitting LED. We'll put this up to 1 volt. There we go. You know, it kind of looks like a traditional LED, does it not? Shooting up there to the right-hand corner. Or not traditional LED, but what am I trying to say here? Diode. But we had the same style characteristic here, okay, as you would with traditional diodes. Our voltage, forward biasing voltage, well, channel 1 is on 1 volt. We can count this out. Let's see, 1, that's 1. And then approximately 2, 4, 6, right there at almost 1.8 volts. We see that as being significant enough to forward bias this diode, since we are producing 6 volts coming from our signal generator. So factually, we've tested out this diode. If you wanted to look up the data sheet on it, but it's kind of written right here. You can see that measurements there. Again, you're going from the very center and then counting outwards. But take it out of XY for a second, and let's make these equal to each other. bring this down. Yeah, I lose quite a bit of amplitude on that in this direction, but if we were to make it look the same, it's essentially the same thing that you have for an LED. You know, as your voltage begins to drop, the LED stops to conduct. It's no longer biased. There's no current flow. And as our voltage starts to increase, now we got current again. Now, if you remember, when you look at a diode after doing a video recording, it looks like it's flickering. That's essentially what's occurring here, because this is happening, you know, at whatever at whatever frequency we've applied. You know, we're at 100 hertz, so the inverse of that is let me do some quick math here. Well, if we take the inverse of our frequency, we're going to come up with 10,000 microseconds. So that on-off time, you know, one full cycle or period, you know, basically completing the entire period, is going to occur every 10,000 microseconds. So that's how quickly we have these changes in state from on to off to on to off, back to on, and vice versa, etc. Anyways, you see it as flicker when you're recording using a video, versus on here we can see it on an O-scope. Take it back to XY format. Again, when you are doing making a test with these, you want to make sure that your O-scope is set up to how you would like to view the item. Okay, so if I wanted to keep it at 2 volts and then 500 millivolts for channel 2, I'd keep it there when I test, say, a replacement item to see if that component is good or bad. But I kind of also want to test one other thing, just to see if it makes, what difference it makes with what we see on our display. I have these pretty cool color flashing diodes that change color, so that should change, may create a change with our forward biasing voltage as our colors shift. Let's see what occurs. I'll hook this up and hook up over here. Ooh, and look at the characteristic of this LED. We actually have a forward biasing voltage and a reverse biasing voltage. Let's move this out a bit. This might be a little bit better to view here. Let me come out of my XY mode. Ooh, look at that. And we can see that reverse biasing voltage also having an effect on our ability to conduct in here as well. But anyways, just something cool to annotate. Now, if this was not on alternating current, if it was just on a DC source, you see that all 3 colors are kind of illuminated on this mat here. Maybe I can kill the lights for a second. It actually cycles through all 3 colors and then starts to blend them, the different colors, to make new colors. But you kind of have a rainbow pattern, if you can see that right there. Hopefully this comes through pretty well. You got your greens, your blues, your yellows, your reds, kind of orangish colors as well. I don't know, I just like playing around with things, and this is just something cool. I have not done this to to an LED as such before, so this is much fun for me as hopefully as it is fun for you looking at this. Anyhow, light coming back on. Anyways, again, you know, no different than before. Essentially, you're looking at one component. You can make some measurements with it, although the automatic measurements functions do not work on my oscope. I would need a bare oscope for that. And you can compare the Lissajous pattern to see if the component you're testing looks the same as a known good. And then obviously, you know, if you have an open or a short, you would see those differences as they would appear on your oscope. Well, we can, I don't have an inductor to test, but we can look at some transistors. Let's see, this first one I have right here is this is a 3904, 2N38904. This is a NPN transistor, rated for 40 volts. So NPN meaning the base. Here goes emitter, base, collector. So the base would need to be biased with a positive voltage. And then we can check base to emitter to see if it is conducting. But you can see when it comes to the junction of a transmitter, it's almost like two diodes where either the anode or the cathode are facing each other. But anyways, you can tell with this one, positive to base, and then our other probe to the emitter, that we are conducting. Now if I take the negative probe and I put it over to the collector, we also have that, we can see that as conducting. And then if we wanted to test it for a short, we can go emitter, collector, and yeah, flat line there, because it's reading like an open, as it should, without the base being biased. So we can use this for testing transistors as well. Now we can do the same for what is this one? A 2N 3906. This is a PNP transistor, meaning that the base we need to pull low. Again, same configuration as the previous one. It will be emitter, base, collector. Now let's check emitter to base. Yeah, that looks good. Let's check emitter to, base to collector. And yeah, they're conducting. Now, what if we did emitter to collector? Is it conducting? No, it is not. So good. So we don't have a short on this transistor. Now, something to keep in mind, might be worth noting, is there is a period in which you can cause a transistor to essentially reverse bias as well, and by swapping the polarity to the base of our transistor, we can see that now we have that downward hook. But again, this could be a handy tool for testing out your transistors. And then of course you can also again look at the forward biasing voltage to see how it compares with the data sheet for that transistor. You can test to see if your collector to emitter short as well. So this does serve other purposes as such. And I think it's just a really nifty little tool to have around when you're troubleshooting components and you're concerned, does this component work or does this component not work? And if you'd rather go off of a visual display versus something that you can see lines, a pattern, a curve, curve tracer, then it's certainly within reason to use this method versus just taking a multimeter to test out components. Well, there we have it, folks. A really nifty component tester, in my opinion. Something that affords you more abilities on your oscilloscope, and hopefully this instructional video wasn't too incoherent, because I do get lost in my thoughts sometimes when I'm trying to verbalize things. But hopefully you can see the benefit of making one of these yourself. Definitely something to add in your repertoire if you own an oscilloscope, and if you own an oscilloscope as a technician or an engineer, for doing a few things when it comes to component testing, either determining if the component is good, measuring it with a known good and a known bad, and or a suspect bad component, looking at the characteristics of its waveform, as we saw on the oscilloscope with its trace and different what we term forward biasing voltage or reverse biasing voltage, and then you know, short and open detection as well, and hopefully you'll see the maybe yourself, if you followed along, you can build one yourself and use it as you are troubleshooting electronic equipment. But anyways, I'm probably rambling on a bit now. I've really enjoyed doing this. Hopefully you've enjoyed watching this. Thank you for your time. Take care. Goodbye.
Mark?